Good evening, everyone. Welcome to today's week 11 live interaction session for the course Fabrication Techniques for MEMS-based sensors from the clinical perspective. I'm the course TA, Rehan Jasna. This is about me, and every week on Monday from 6 p.m. to 8 p.m. we'll be having this live session. This is a meeting link, and in the YouTube channel I'll be uploading the recorded videos, and this is a Google Drive link. So first, let us start with recap of whatever content that was covered in week 11. So in week 11, we saw about some of the equipments that are used in clean room, such as stereo microscope, metallurgical microscope, inverted microscope, fire alarm, and biosafety hood. So we saw that like so some of the microscopes. So what we saw was like the stereo microscope, the metallurgical microscope, and the inverted microscope. All three use optical uh, light in order to visualize the sample. And the visualization happens either based on the transmission of the light or the reflection of the light from the sample. Okay. Then we saw like how fire alarm is like how it is placed in a lab. And we also saw about biosafety level benches. So now let us move on to some of the problems regarding the content that was covered in uh, week 11. The first problem is identify the odd one based on the type of beam applied on the sample. Option A is compound microscope, B stereo microscope, C inverted microscope, D electron microscope. So you have to find which one, like which is the odd one out, and the hint that is given here is that the type of the beam that is applied on the sample. So which one do you think is the correct answer? Okay, the correct answer is option D, electron microscope. Okay, so like these three, as we see, the compound microscope, the stereo microscope, and the inverted microscope. These three microscopes are based on like the visualization happens by from the optical light. So from the name itself, you can see that we'll use electrons or electron beam in order to visualize the sample. Here we are using an optical beam. Okay. And if you see the inverted microscope, it's based on the transmission of light. So the correct answer here in problem 1 is option D, electron microscope. Now let us move on to the next problem. Problem 2. A good practice is to disinfect the biosafety hood before use. Hence, an efficient sterilization method would be option A, hot air thrust, option B, HEPA filters, option C, UV rays, option D, antibacterial wipes. So this question is about the biosafety hood. So we already know that the biosafety hood is used to uh, handle the samples, biological samples, and there are already like different levels depending on what biosample we are handling. So before and after we use the hood, we want to protect ourselves, the environment, as well as the sample from being contaminated from other places. So that's why we have to disinfect the biosafety hood before and after use. So which one of the following techniques will be used to disinfect the biosafety hood? Which is the correct answer? So the correct answer here is UV rays, option C. So generally in biosafety hoods, they will use ultraviolet radiation uh, to disinfect uh, the samples. And this technique, they call it as ultraviolet germicidal irradiation. So in short, they call it as UVGI. Ultraviolet germicidal irradiation. So, so in this technique, they generally use UVC light, which is having the wavelength of 180 nanometer to 280 nanometer to kill or to inactivate any microorganisms. So how does this UV radiation kill the microorganisms? When the microbes are exposed to UV radiation, their genetic material gets damaged. So like this will prevent them from carrying out any vital function. And like what happens in an ultraviolet disinfection system is that the uh, UV radiation will penetrate the cell wall of the organism, and then it will like destroy all the vital functions, including the multiplication, cell multiplication, and so on. So this UV light generally affects the nucleic acid, either DNA or RNA. Now let us move on to the next question. Problem 3. if 10x is the ocular power of a metallurgical microscope, what should be the objective power to get 400x magnification? So option A is 40x, option B is 4000x, option C is 400x, option D is 4x. So ocular lens is the eyepiece lens. So which is the correct answer? Okay, so the eyepiece lens is called as ocular lens. So what it will do is it will just magnify the image that is provided by the objective lens. So what happens is like we can consider it as having two lenses. The first image that is produced by the objective lens will be magnified by the ocular lens. So if we want to find the overall magnification of the system, we can multiply the individual magnification. Okay, so this will be magnification of objective lens into magnification of ocular lens. So overall we are getting 400x magnification. Objective lens, we don't know what is the magnification of the objective lens. So we know that 10x is the ocular power of the metallurgical microscope. So from this you can say that the objective power is 40x. So the correct answer is option A, 40x. Is this clear? This is clear? This is clear. Now let us move on to the next problem. The turret is found below the stage in option A, metallurgical microscope, option B, stereo microscope, option C, inverted microscope, option D, electron microscope. So in which microscope do you find the turret? What is the correct answer for this question? So the correct answer for this question is option C, inverted microscope. Okay, so what is a turret? So here you can see this is a compound microscope. Okay, so the turret of a microscope is just a rotating metal ring that will hold the microscope objective lenses. So here you can see that this microscope is having multiple objective lens, uh, each with having a different power of magnification. So we can by having this turret, we can easily change the magnification level by switching between each of like different objective lenses. So that is what a turret is. Okay. So now let us see the how like each microscopes look like. So this is how an inverted microscope looks like, and here you can see like you have to see where the objective lens is, right? The objective lens is down here. So the objective lens is here. So that is below the stage. This is a stage. Okay. So in this, what is asked is the turret is found below the stage in which microscope, right? Option A, metallurgical microscope. Option B, stereo microscope. Option C, inverted microscope. And option D, electron microscope. So here you can see that in these four options, like it is not electron microscope. Why? This is because turret is on a microscope is just a rotating metal ring that will hold the microscope's objective lens. So that is what a turret is. So what is the function of this turret? This is to just change the magnification level by switching between different objective lenses. So like we don't use any like switchable objective lens in the case of an electron microscope. So that's not the answer. And here you can see image of a compound microscope. Okay. So in this compound microscope, here you can see there are multiple objective lenses, and all these objective lenses are attached or they are held together by means of a turret. So that is the objective turret. This is just to switch between the different magnification. So we have to find which microscope is having the objective lens below the sample stage. So if we look at the inverted microscope, here you can see this is our objective lens and this is our stage. So the objective lens is below the sample stage, and here we will have a turret so that we can switch between the different magnification of the objective lens. So this is the image of a compound microscope. Here the turret is above the sample stage. So the correct answer is not a compound microscope. And in the case of a stereo microscope, you again see that the objective lens is above the stage plate. So this is also wrong. This is how a metallurgical microscope looks like. And here also you can see that the objective lens is above the sample stage, right? So this is the turret. So the correct answer for this problem 4 is a turret is found below the stage in inverted microscope. Option C. Now let us see problem 4. The turret is found below the stage in option A, metallurgical microscope, option B, stereo microscope, option C, inverted microscope, and option D, electron microscope. So now let us move on to the next problem, problem 5. The type of pressure modules used in HEPA filters are option A, positive, option B, neutral, option C, negative, option D, atmospheric pressure. So which is the correct answer for this one? So the full form for HEPA filter is high efficiency particulate air filter. So this filter is generally used in clean room in order to like have a good control on the number of particles that is present. So it is generally a mechanical kind of filter. So there is a type of pressure module that is used in HEPA filter in order to bring about the filtering process. So this we saw, I think, in last week's question as well. Okay. So the correct answer for this question is positive pressure. Let me tell you why. So like in clean room, there are different types of clean room. One is positive pressure clean room, and another is negative pressure clean room. In positive pressure, like what do we mean by positive pressure? Positive pressure is when the pressure inside the clean room is greater than the atmospheric pressure. So there is a particular reason why this kind of pressure module is used in HEPA filter. So like if you consider an air balloon, like if you are blowing air inside a balloon, as you blow more and more air inside the balloon, the pressure inside the balloon will increase compared to the atmospheric pressure, right? And let's say you stop blowing the balloon and you are leaving, like letting the air come out from the balloon, then what happens is you will see the air flowing from inside of the balloon to the atmosphere. That is, air is flowing from a region of high pressure to a region of low pressure. And if you like see, there will not be any airflow in the opposite direction. Like you will not see air flowing from low pressure to high pressure. So like this is a natural like natural phenomenon. So we are using the same principle in clean room where we maintain it at higher than atmospheric pressure, which is positive pressure. So outside the clean room, we'll have negative pressure. Sorry, not negative pressure. We'll have the atmospheric pressure. So air will generally flow from region of high pressure to lower pressure. So whatever air is there, it will flow outside. This also prevents the like external air from coming inside. In case there is any leak or breach in the clean room environment, like the air will flow from inside the clean room to the outside, not in the reverse direction. Thereby, we can reduce the particle contamination and and these kind of phenomena we can reduce. So that's why they are using positive pressure module in clean room and in the HEPA filter. So now let us move on to next problem, problem 6. Okay. Now let us look at problem 6. The most commonly used biosafety cabinet for working with biosamples is option A, class 1, option B, class 2, option C, class 3, option D, and class 4. So which is the correct answer? So the correct answer for this problem is option B, class C. Hmm. We already saw similar, like we saw intro to biosafety cabinets in the previous week. So what is a biosafety cabinet? A biosafety cabinet is a primary containment device which is used with for handling biological material. So we are having like we will handle the biological materials in some enclosed workspace where we have a ventilated hood in order to contain the pathogenic microorganisms, like while during any processing of the sample. The US Centers for Disease Control have classified the biosafety cabinets into different levels depending on the hazardness of the biosafety cabinet. And each level will have certain performance characteristics. So there are three biosafety cabinet levels. One is class 1, class 2, and class 3. So class 1 and 2 are used for biosafety levels 1 and 2. And class 3 is generally biosafety cabinet is used for biosafety levels 3 or 4. So here as the biosafety level increases, we are dealing with more harmful pathogens organisms. So the so class 3 will be like handling very dangerous pathogens. The commonly used biosafety cabinet is class 2. So in class 2 cabinet, we can handle both class 1 and class 2 level biosafety level samples. Is this clear? Is this clear? If it is clear, we can move on to the next problem. Objective lens, electromagnetic condenser lens, backscatter detector, and secondary electron detector are part of option A, scanning electron microscopy. Option B, transmission electron microscopy. Option C, both scanning and transmission electron microscopy. Option D, stereo microscopy. So which is the correct answer? So which is the correct answer for this problem? The correct answer for this problem is option A, scanning electron microscope. Okay, I'll tell you why. Um, So here you can see the images of a scanning electron microscope. So this is scanning electron microscope, and TEM is for a transmission electron microscope. Okay. What happens is in a scanning electron microscope, you can see that the electrons are produced at the top of the column by means of an electron gun. So then these are accelerated towards the column at a particular accelerating voltage. So here you can see that the diameter of B. So we have something called as condenser lens in order to reduce the diameter of the beam. Then we also have another lens called as objective lens. This is to focus the beam on the sample surface. Then here you can see this is a sample and this is kept on a motorized state so that we can move around while we can image different portions of the sample at the same time. In order to like sense the electrons, we have like different kind of detectors. One is the backscattered electron detector, the X-ray detector, and the secondary electron detector. So, like what happens is when the scan electron beam strikes the sample, like the electrons will interact with the sample and it will generate different kinds of like products such as secondary electrons, backscattered electrons, and X-rays. So for detecting each of these particular scattered electrons as well as secondary electrons and X-ray detector, we have different detectors. Then this is then given to a scan generator, and we will have some specialized software in computer so that we can get a grayscale image of the sample pixel by pixel. So this is the basic block diagram of a SEM microscope, which is scanning electron microscope. So here in the right side, you can see TEM. TEM also uses a electron beam, but the main difference is that here the electrons will transmit through the sample, whereas in SEM, like the electrons will just like interact with the surface of the sample more rather than not like it will interact with the sample. It will not completely get transmitted through the sample. So, like here we saw that we have three different kind of detectors, right? In SEM, the secondary electron detector. So, this is generated closer to the surface. So, generally, if you want to image the topography of the sample, we'll use the secondary electron detector. If we want to find the composition of the surface, then we'll use a backscattered electron detector. Then we also have X-ray detector, right? So in X-ray detector, we can identify what are the elements present in the sample. So if we look at TEM, here also we have an electron source, and then we have condenser lens in order to uh, reduce the diameter of the primary beam. Then uh, we have a condenser aperture. So this condenser aperture will reduce the beam further, and it will like remove any other electrons which are not along the particular axis. Then the objective lens will focus the beam on the on the sample. Then like this is transmission electron microscope, right? So the electron beams will get transmitted to the sample. We have another objective lens to focus the diverged beam from electron beam from the sample. Then we have other projector lens, intermediate lenses, and objective aperture in order to finally focus the transmitted electrons on a fluorescent screen. So why do we need to use a transmission electron microscope? Why do we need a transmission electron microscope? So like we can use this transmission electron microscopy in order to image like very thin samples. Uh, so so here if you see in the question, whatever that is asked, right? The transmission electron microscopy also has objective lens. It has condenser lens, electromagnetic condenser lens. Okay. However, it does not have the backscatter detector and the secondary electron detector, right? So the scanning electron microscopy is the only one which is having all this. So the correct answer for this problem is scanning electron microscopy. Now let us move on to the next problem. This is how a stereo microscope will look like. So it uses optical light to image a sample. Now let's go to the next problem. Problem 8. Light source used in microscope can be option A, tungsten or halogen lamp, option B, mercury vapor lamp, option C, xenon lamp, option D, all the above. So what is the light source that is used in a microscope? What is the correct answer? What's the correct answer for this problem? What light source are we using in the microscope? Okay. So the correct answer for this problem is D, option D, all the above. So in olden days, what they did was that they used an oil lamp and natural sunlight in order to uh, like provide an external source of light for their like primitive microscopes. However, like it is not a reliable illumination. So in modern microscopes, we have a integral light source and that is controlled. So there are like different types of light sources that are commonly used. One of them is a tungsten halogen lamp. Okay. So one of the light sources that was used was a tungsten halogen lamp. So like the tungsten halogen lamp has a bulb that will operate on DC voltage and like for illumination it will take some amount of power. So one disadvantage of this tungsten halogen lamp is that it will generate large amount of heat during the operation. So it will the like lamp assembly setup will have large number of heat sinks in order to dissipate the heat. So later, like there were also microscopes where they had used incandescent lamps. So they used incandescent tungsten-based lamp. In this, like there will be a bulb, okay, enclosed bulb, and this glass bulb will be filled with some inert gas like any halogen gas. Later, people moved on to incandescent lamps. In incandescent lamp, what we'll have is we'll have an enclosed glass bulb that is filled with an inert gas, and it will have a tungsten wire filament. So in incandescent lamp, like this, they had an enclosed gas bulb which is filled with some inert gas, and there'll be a tungsten wire filament. So when like DC electric current is passed through the filament, the bulb will produce a large amount of heat and light. So this also like with age the intensity will decrease, and like as the heating happens, like the tungsten the filament will start getting evaporated. So like inside the bulb it will start darkening. So that was one of the disadvantage of using a incandescent lamp. So people also used mercury vapor lamp and xenon lamps. So in these lamp, like what we are doing is we will ignite the lamp Then we will provide the suitable amount of current to maintain like constant illumination. uh, and vapor mercury arc lamps or mercury vapor lamps, like they have like high intensity in certain wavelengths. Okay, so generally mercury vapor lamp, they are in near UV wavelength, and so some of the wavelengths are 313 nanometer, 334 nanometer, 365 nanometer, 406 nanometer, 435 nanometer, and 578 nanometer. So, like generally, mercury vapor lamp is used only for fluorescence, like microscopy, not for other microscopes. However, like xenon lamp have more intensity than mercury vapor lamp. So, their intensity is mainly in the infrared region. High intensity is in the infrared region. So for these kind of lamps, we will need like cooling setup as well. Other than the three light sources that are mentioned here, like laser light source is also one of the light sources that has been used in some microscopes. So is this clear? Now let us move on to the next problem. Problem 9. So in problem 9, using lift-off technique, platinum interdigitated electrodes with 5 micron features are patterned on a 3-inch silicon substrate. As silicon substrate is opaque in nature, the features can be better visualized under option A, inverted microscope, option B, metallurgical microscope, option C, stereo microscope, option D, compound microscope. So which microscope is used, will provide us the better visualization? And here one important thing that is mentioned is that the substrate is opaque in nature. So which microscope do you think is better suited for this function? Okay, so let us look at each of the options one by one. Okay. Okay, so now let us look at each of the options one by one. So the first option is what? Inverted microscope. So this is how inverted microscope looks like, right? So in inverted microscope is generally very popularly used for live cell imaging. And what happens is like we will have a cell culture vessel which we place it here, and then we see the images from the bottom of the vessel. Why do we need to see images from the bottom? That is because most of the like we will keep cells in a particular culture medium, so the cells will naturally sink to the bottom of the vessel, or they will just attached to some surface and they will start to grow in that surface. Mm. If we try to image from the top side, what will happen is that like it will be difficult to focus the because there will be some liquid on top of the cells, so it will be really difficult to focus the sample. And also, like while focusing, we don't want the objective lens to come in contact with the sample, right? So for those reasons, we use like inverted microscope while imaging any live cell culture. So here we want to image a opaque substrate, right? So next is compound microscope. A compound microscope is one of the options. So in compound microscope, we have objective lens. We also have a condenser lens. So here in compound microscope, like it has two sets of lenses. In order to get a higher magnification than stereo microscope, and one important thing is that the magnification range is generally in the range of 40x to 1000x, right? So in compound microscope, what happens is that the magnification that is provided by the objective lens will get magnified by the lens in the eyepiece. So that's why they call it as a compound microscope. That is, it is getting multiplied. So compound microscope can also be used to visualize biological samples, like from the top, like which is kept on slides, and like you can see phase contrast images for looking at samples of bacteria or blood cells. And also, like if you want to examine minerals or thin slice of rocks, like we will use some polarizing, uh, like we will try to polarize the light in order to pick up the difference in the color. So for that purpose also, we use a compound microscope. Next is stereo microscope. So what is the difference between a stereo microscope and a common microscope is that in stereo microscope we have only one set of lens. In compound microscope we have two sets of lens to get a higher magnification than a stereo microscope. Then stereo microscope can also provide us with a 3D image. However, it will give a lower magnification, like less than 40x. So 10x to 40x is the magnification that it will provide. So the last option that we have here is metallurgical microscope. So stereo microscope, as you see here, it is also called as dissecting microscope. So what it will do is it will try to image a sample by means of light that is reflected from the specimen. So generally we use this type of microscope for seeing any dissected samples. And here if you see the eyepieces, like like we will get light path from different angle of viewing. So this will help us to get a 3D image of the sample. And like so we will be able to perceive the depth as well. So while dissecting any samples, we'll generally use the stereo microscope. So the last option that was given in the question was stereo microscope. The last option that the other option that was given in the question was metallurgical microscope. So here you can see a metallurgical microscope where you have like objective lenses, a polarizer as well. So in metallurgical microscope, what will happen is that like they use the principle of reflected light in order to image a sample. And we use generally to view opaque objects, so metallurgical objects, and like objects in which like light will not pass through the sample. So this is generally suitable for non-transparent materials like metals, rocks, and so on. So how one example is like if you want to visualize different rocks, uh, we can change the polarization and light intensity by means of filters that are placed here. So that is one like thing you will not see in the other microscopes. Okay. So if you want to image the interdigitated platinum interdigitated electrodes on silicon sample, then the best choice will be to use a metallurgical microscope. Okay. So the correct answer for this is option B, metallurgical microscope. Okay. So now let us move on to next question. Problem 10. The type of detectors that must be furnished in every laboratory to detect fire hazard is option A, water, option B, smoke, option C, nitrogen, option D, light. So what detector do we use to detect the fire hazard? Which is a detector that we'll use to detect the fire hazard? The correct answer is smoke detector. So if there is a fire, then there will be definitely smoke coming out. So with that, we can detect the fire hazard. Now let us move on to the next problem. Problem 11. Usually the working distance increases with increasing magnification. Is this statement true or false? So this is related, this question is again related to microscope. Is this statement true or false? Okay. So the correct answer for this question is false. So, like in the second figure, first let us look at the second figure. So here we have a microscope which is having an objective lens, and like what is working distance? Working distance is the distance between the bottom of the objective lens to the like sample. So here is where we will place your sample. This is your objective lens. So the distance between the bottom of your objective lens to the top of the sample, and this distance is when the sample is in sharp focus. Okay. So if we look at the first figure that you see here, here we are having an optical system. Okay. So if we look at first figure, here is where we are keeping our sample. Okay. This is where a sample is present. Now, like we have something called as a field of view. So this is how much, like it will capture this amount of image and uh, in the optical system. So if when we increase magnification, what will happen is your field of view will decrease, right? That is your depth of field will decrease. And like if your depth of field is decreasing, then your working distance will um, also decrease. Like here, you can see that this is a field of view. That is how much like you can view. So if when you increase your magnification, what you can see is in microscope you will be able to see like less amount of the sample, right? So your field of view will decrease as you increase your magnification. Okay. So like as your field of view decreases, in order to focus your sample, then your working distance will also have to decrease. Okay. However, like you will see that in a microscope, in compound microscope, there will be multiple objective lenses, and on the objective lens, they would have mentioned what is the working distance. Like different manufacturers may have different working distance for the same type of magnification. Okay. So that is that is possible. Is this clear? So the answer is false. That is because the working distance will decrease with increase in magnification. Now let us move on to next problem, problem 12. Suppose an image is taken by a microscope with light passing through the following objectives: 5x, 10x, and 100x. Find the effective magnification. So we saw a similar question earlier, right? What is the answer for this question then? So here we know that the total magnification is product of the individual magnifications, right? Let's say we have three lenses, right? M1 into M2 into M3. So it will be 5 into 10 into 100. 5000x is the effective magnification. So is this clear? Now let us move on to the next problem. Problem 13. Which of the following types of microscope enables 3D perception of the subject by gathering light from two optical paths? Option A, compound microscope; B, stereo microscope; C, inverted microscope; D, electron microscope. So, which is the correct answer for this? Which is the correct answer for this problem? The correct answer is option B, stereo microscope. So here you can see a stereo microscope, okay, where you are having objective lens. So in stereo microscopes, like we have a low magnification power compared to that of compound microscopes. Then another thing is that it will image the sample based on the light reflected from the sample. So generally we use it for viewing dissected samples. It will provide some like depth information as well. So what happens is that we have the microscope eyepiece as well as the microscope objective lens. So there will be light coming from the objective lens as well as light will be coming from the microscope as well. So here you can see that the distance is different, right? So light will travel in two different paths. One is along the objective lens and one is along the eyepiece. And also you can see that like it is in two different angles. So this is somewhat straight, this is kind of bent. So we will have different angle of viewing as well. This will enable us to have 3D like visual because like each like since we can since the light is then traveling along different angles, we can see the like since the light is traveling along different angles, we'll be able to see a 3D visual of the sample. So so what happens is that in stereo microscope there are two optical paths for each eye. One is along the eyepiece and the other is along the objective lens. So here you can see the objective lens and since the distance like you can see the path is different, so the distance traveled by the light is also different. The angle in which the light is traveling is also different. Okay. So based on combination of all these, we'll be able to see like image in 3D view. However, this has like lower magnification, less than 40x. So it's generally used for viewing dissected samples, like I mentioned before, because it will also give us the depth, like some kind of visualization with respect to depth. Okay. So the correct answer is option B, stereo microscope. Now let us move on to next problem, problem 14. Problem 14. Resolving power of a microscope is a function of option A, wavelength of light used, option B, numerical aperture of lens system, option C, refractive index, option D, wavelength of light used and numerical aperture of lens system. So which is the correct answer? Okay, what is you would have heard of resolution, right? Have you heard of what is the resolving power? Okay. So resolving power is this like it will tell us the smallest detail that a microscope can resolve while imaging a specimen. Okay. So resolving power is generally inversely proportional to resolution. So if you look at the Rayleigh formula for resolution, Rayleigh formula resolution is 0.61 into lambda divided by Na. So here lambda is wavelength of the light, Na is numerical aperture of objective lens. Okay. So we can say that our resolving power is numerical aperture divided by 0.61 into lambda. Okay. So what is aperture? Numerical aperture is like how much the objective lens or any particular lens can gather light. So I think in one of the like previous image we saw that light is like a beam of light which is coming like this is gathered, right? So like here whatever numerical aperture that we are finding is related to the angle of this cone. And if you want to find the formula for numerical aperture, then it is related to refractive index as well. So it is numerical aperture is Na into sine theta. N is refractive index of the material. Refractive index of the medium between sample and lens. So like to summarize, if we look at resolving power, it depends on wavelength and also it depends on numerical aperture. This numerical aperture depends on refractive index. So the correct answer for this one is wavelength of light used and numerical aperture of the lens system. If it is a multiple like correct answer, then refractive index also will come, right? So numerical aperture is related to refractive index. So this is correct. Option D is correct. Now let us move on to next problem. Problem 15. The greatest resolution in light microscopy can be obtained with option A, longest wavelength of visible light used. Option B, an objective with minimum numerical aperture. Option C, shortest wavelength of visible light used. Option D, shortest wavelength of visible light used and objective with maximum numerical aperture. So which is the correct answer for this one? So already in previous problem while seeing we saw that the resolution, right? Resolution is given by 0.61 into lambda divided by Na. Okay. So if you want like to resolve very small features, you should have a very high uh, numerical aperture and small wavelength. So the correct answer is option D. Shortest wavelength of visible light used and objective with the maximum numerical aperture. And also if you compare optical microscopy with like electron microscopy, you will see that the resolution for electron beam microscopy is even smaller because the wavelength of the electron beam is even smaller compared to the wavelength of the visible light spectrum. And if you are using X-rays for imaging, then the wavelength is even small. Okay. So here again, numerical aperture, it is related to n into sine theta. N is refractive index of the material between the objective lens and specimen. And theta is the angular aperture. So if you are having your sample here and your objective lens is like this. And for your particular working distance, let's say this much of your sample is getting viewed. Then this theta will be the angular aperture. Now let us move on to next problem, problem 16. Which part of the compound microscope helps in gathering and focusing light rays on the specimen to be viewed? Option A, eyepiece lens. Option B, objective lens. Option C, condenser lens. Option D, magnifying lens. So this is in a compound microscope. Like we are, what we are doing is we already know that we are having a light source. So which like part are we using to gather and focus the light rays on the specimen? So we know that in a magnification system, there are like different types of lenses. Like you can see in these options that are given here, and each of these lenses will have a specific function. So first, let us start with the objective lens. Okay. So what is an objective lens? An objective lens is like something that is present in the compound microscope, which will provide a like real inverted image of the sample. So this will provide the first step of magnification. So depending on the power of the objective lens, the like if the objective lens is having higher power, then like the magnification also will be higher. Ocular lens is known as eyepiece lens. So what this eyepiece lens does is that it will the objective lens it will provide the primary magnifying magnification, and it is generally very close to the sample that is being observed. So what it will do is it will capture the light from the sample and it will magnify while making the sample in focus. So then the eyepiece is like it is also called as ocular lens. It will magnify the image that is produced by the objective lens. So this will provide you a secondary step of magnification. Magnifying lens as a name, it will be used to provide magnification of the image, right? So what is condenser lens? A condenser lens is generally used to gather the light rays that are coming from different angles, like from the light source, and like make it into a focused beam. So here you can see that we are having two types of systems. Okay. So what is the function of a condenser lens? Here you are seeing like two types of images, right? In the first one, we are having only the objective lens. So this is a screen. Okay. Here you are having your light source. So if you see the objective lens will be able to capture only like some amount of diffracted light, a narrow diffracted light, depending on the aperture angle for the objective lens. So when we are having a light source which is like a parallel beam, like when it is getting incident on the sample, the light will get diffracted in different directions. However, in objective lens, we cannot visual like due to the effect of numerical aperture of the objective lens, we cannot visualize like it cannot capture all the diffracted light beams. Okay, so like we will not get good resolution as well because of this. However, if we are having a condenser lens in this assembly, then what will this condenser lens do is that it will try to converge the parallel beam of light from the light source into a straight path. So it will try to reduce the aperture of the light, and what this will do is this will help you like to focus the light on certain regions of the sample, and like it will also help you to make the maximum amount of light to reach the projector lens, that is to reach the screen. Mm. And if you see like when you are adding a condenser lens with an objective lens, then your numerical aperture also increases, so you are able to view more. So uh, as a result of this, what will happen is that the resolution of the system will also increase. So generally, to say in short, the condenser lens helps the objective lens to gather light rays like from larger diffraction angle, and like this will increase your numerical aperture of the system. As your numerical aperture increases, your resolution also will increase. Now let us move on to problem 17. Which part of the light microscope controls the intensity of light entering the viewing area? Option A, coarse adjustment screw. Option B, fine adjustment screw. Option C, diaphragm. Option D, condenser lens. So here, which is controlling the intensity of light entering the viewing area? Means of the uh, from the light source of your microscope, which part is controlling how much light is falling on the sample? So we know that it's not the condenser lens. We have two other options: coarse adjustment screw, fine adjustment screw, and diaphragm. So the correct answer is option C, diaphragm. Okay. So here you have a microscope, and in this microscope, like the condenser, this is a condenser lens, right? So this lens will focus the light like to fall on the sample. So here we have something called as a diaphragm lever. And if we look at the diaphragm of a microscope, this is how it will look like. So like it will be present along the illumination pathway, and it will regulate the amount of light that is reaching the sample by controlling the size of this aperture. So if the size is large, then it will allow a large amount of light to reach the sample. If the size is small, then it will allow only small amount of light to reach the sample. And what it does is it controls the brightness, contrast, and depth of field. So it controls these three things. So like by adjusting these things, we will be able to get a more precise and detailed image. Right? So we'll get a high quality image. So the correct answer for problem 17 is option C, diaphragm. Now let us move on to next problem, problem 18. Which of the following microscopes work based on transmission of light? Option A, metallurgical microscope. B, stereo microscope. C, inverted microscope. So this is a direct question. Which of the following microscopes work based on transmission of light, not on reflection of light? Okay. So the correct answer is option A, metallurgical microscope, and option C, inverted microscope. So the the stereo microscope is generally reflection based. So it images based on the reflection of light. Now let us move on to next problem, problem 19. Suppose that your eyepiece provides a 10x magnification and objective is set at 20x magnification. What is the overall magnification at which you see the sample? So this is similar to previous question. Option A is 10x, B is 20x, C is 200x, D is 30x. So, like we know that the objective lens will provide us with the primary magnification of the sample. Then the eyepiece lens will provide you a secondary magnification. So it will magnify the image that is provided by the objective lens. So the total magnification will be product of your individual magnifications. So it is 10 into 20, which is 200x. So the overall magnification is option C, 200x. Now let us move on to next problem, problem 20, which is the correct sequence, the light of light in decreasing order of energy. So here, sorry, uh, which is the correct sequence of light in decreasing order of energy? Option A is blue greater than green greater than yellow. Option B is blue greater than yellow greater than green. Option C is yellow greater than green greater than blue. Option D is yellow greater than blue greater than green. So which is the correct answer for this question? So you know that like for light, like the colors of a rainbow is Bibgyor, right? Bibgyor. So in this, like the red has the highest wavelength and violet has the lowest wavelength. So if you want to see the energy of the wave, that is energy is equal to h into nu. H is Planck's constant and nu is the frequency. So frequency is c divided by lambda. So c is velocity of light or speed of light and lambda is wavelength. Right. So like if it is having higher wavelength, then it means it has lower frequency, which means it has lower energy. Okay. So this is the highest wavelength. So we can say it is low frequency. This is high frequency, low energy, and this is high energy. Okay. So if you are looking in terms of energy, blue greater than green greater than yellow. So the correct answer is option E. So here you can see the electromagnetic spectrum with like specific focus on the visible region. And in here you can see the wavelength, right? So for larger wavelength, your like if your wavelength is large, then your frequency is small. If your wavelength is small, then your frequency is large. Okay, the values are given here. And this is your Vibgyor spectrum. So your this is violet, this is red. Red is having large wavelength. Violet is having the smallest wavelength. So smallest wavelength, small frequency. Sorry, smallest wavelength, large frequency. Large wavelength, small frequency. Okay. So from that, like we know the energy of the electromagnetic wave is E equal to h into nu. Nu is the frequency. So from that you can find out what is the energy of each of the wavelength of light, for each of the visible color. So the correct answer is option A, blue greater than green greater than yellow. Uh, is this clear? Now let us. Are there any questions? Are there any questions? If not, we can end the session. Thank you.